let us look at this matrix. A is equal to 2, negative 5, 1, negative 4. We are to determine the eigenvalues for this matrix. Well, here, well, I think this should be off rather than for. The value of the matrix, value of. All right. Now, if you have been practicing finding the eigenvalues of matrices, then you should be able to work this one out. So pause the video, write the question down, and make your attempt at it. Okay, so you have done that. What was your solution? Right? Remember, you learn by doing. You must practice. You learn by doing when it comes to mathematics. All right. Now, let's talk about this. Now, remember, we're not going to rush working out the question as if we were in exam. Right? I'm going to assume that maybe you don't remember the steps, or well, you should have looked up the steps even as you pause the video and make your attempt at it. But let's look at the arguments behind finding the eigenvalues. Remember now, you have a matrix A times its eigenvalue x, and remember, eigen means German. So a matrix times its own value. Eigen means own in German. All right. So a matrix multiplied by its own value. X is not the value, x is the vector. A matrix, this matrix A multiplied by its vector, its own vector, its eigenvector, is equal to the eigenvalue of the matrix, which is lambda, times its own vector. So instead of using this big matrix and working on it, transforming it, multiplying by its vector, what you can do is use its value times its vector. All right. Now, suppose you subtract both, make both of them on the left equal 0. What you're saying is that the matrix times its own vector, its eigenvector, minus the eigenvalue of the matrix times its eigenvector is equal to 0. All right. Now, factor out the eigenvector. X times the matrix minus its eigenvalue is equal to 0. But hold on, let's see something here. You see the matrix A, it's in the form A, B, C, D, all right? Where A, B, C, and D are numbers, just like here. You have 2, negative 3, 1, 4. The eigenvector of the matrix is in the form, maybe call it EF, since we use those other letters already. But lambda is equal to a scalar G. So what you're saying, well, in order to deal with this, you have to put the vector on the right hand side. So rewrite it, A minus lambda times x equals 0. This is in the form A, B, C, D minus lambda times what we'll call it, EF, two numbers here, equals 0. But hold on. You're trying to say that you have a matrix minus a scalar. That can't work. Right? It's like you're using the matrix 2 negative, well, it was negative 3, it's negative 5, 2 negative 5, 1 negative 4. 2 negative 5, 1 negative 4. Minus 6, that can't work. You can have a matrix minus a matrix. You could have 2 negative 5 negative 4 minus 6 0 0 6. So 2 minus 6, then 5 minus 0, then 1 minus 0, then 4 minus 6. So here, what you can say is that lambda cannot remain as a, well, lambda is a scalar. Lambda cannot remain by itself as it is a scalar. Right? What you must do, multiply it by what we call the identity matrix or the unit matrix, which is equivalent to 1 when you're dealing with numbers. And that matrix is 1 0 0 1. All right. So you have A, B, C, D, the general matrix, minus lambda times 1 0 0 1. It's the same thing as A, B, C, D times lambda 0 0 lambda. All right. So that now can work, because you'd have A minus lambda, B minus 0, C minus 0, D minus lambda. All right? So what you must have is A minus lambda I times x equals 0. A minus lambda I times x equals 0. Good. Now, suppose you look at this and you say, how do you find x? Well, if these were numbers, you could divide both sides by a minus lambda I and say x equals 0 over a minus lambda I. But x would be 0. You would be saying that the eigenvector is 0, which wouldn't make sense. Right? If all the eigenvectors were 0, you'd already know that all eigenvectors were 0, and you would have to go through all of this work to find the eigenvector. Now, here, you can't do that as if you're dealing with numbers. What you'd have to do is multiply both sides by the inverse of this matrix. So multiply by a minus lambda I inverse. So you say a minus lambda I times A minus lambda I inverse times X is equal to 0 by A minus lambda I inverse. That's what you'll have to do. Alright? Or you can't really just take a number over a matrix like that. Now here, this, a matrix times its inverse, is a unit matrix. Alright? Now, if you could do this, you would have 1, 0, 0, 1 times X is equal to 0 times A minus lambda I. Oh my. A minus lambda I inverse, which is 0. 0 times anything gives a 0, right? 0 times all of this would be 0. But that can't work either, because you'll be saying that X is 0. So the argument here is that you should not be able to find the inverse of A minus lambda I. So you cannot find the inverse of A minus lambda I. Now, what does that mean? What do you call a matrix for which you cannot find the inverse? You should remember, it's a singular matrix. So therefore, A minus lambda I is a singular matrix. Alright? So it's a singular matrix. And what do you know about a singular matrix? Its determinant is 0. Alright? So therefore, the determinant of A minus lambda I is equal to 0. Right? That's the argument behind this thing here. Now, I want you to understand the reason why you do what you do when you're working the maths out. Alright? So that's why I spent the time to remind us all, or to remind you of the argument behind working this thing out. Now, if this is the case, A minus lambda I, the determinant is 0. And remember now, A is this. What you're going to have to do now, say since A is equal to, what was it again? 2, negative 5, 1, negative 4. It was 2, negative 5, 1, negative 4. That's A, right? Lambda is just lambda. I is equal to 1, 0, 0, 1, the identity matrix. And what you're going to say is that 2, negative 5, 1, negative 4 minus lambda times 1, 0, 0, 1. The determinant of that is equal to 0. Alright? Now let's look at something here. You have 2, negative 5, 1, negative 4, minus, when you multiply lambda by this, you get lambda 0, 0, lambda, right? Because you remember, when you multiply a matrix by a number, or just a scalar, you multiply the scalar, or the number, by each element in the matrix. Now, that means the determinant of, you can subtract them now. Remember, when you subtract matrices, you subtract corresponding elements. Element in row 1, column 1 minus element in row 1, column 1. That's 2 minus lambda. Then negative 5 minus 0. So we have negative 5 minus 0. We just negative 5. 1 minus 0 is just 1. And then negative 4 minus lambda. Negative 4 minus lambda. The determinant of that equals 0. I will run out of scrolling space. Can't scroll down anymore, so let's just draw a line here and continue the work that we're doing on the right hand side of this line. Oh my, why this thing just jump up like that? Oh, I'm going to have to bend the corner here now. Book up on this part. Alright, so let's continue. Oh, we have to just continue the line. I want to make use of the screen. Alright, so what was it again? 2 minus lambda, negative 5. So we have 2 minus lambda, negative 5. And then 1, negative 4 minus lambda. Alright. So then we have 1, negative 4 minus lambda. Now, what's the determinant of this? Use the AD minus BC part. This time this minus this time this, alright? So it's 2 minus lambda, negative 4 minus lambda, minus negative 5 times 1. And that is equal to 0. The determinant is equal to 0. So let's multiply them out. 2 by negative 4 is negative 8. 2 by negative lambda is minus 2 lambda. Let me write the lambda properly. Negative lambda by negative 4 is positive 4 lambda. Negative lambda by negative lambda is plus lambda squared minus negative plus 5 equals 0. Let's put them together now. We're going to have lambda squared, negative 2 plus 4 is 2, plus 2 lambda, negative 8 plus 5 is negative 3 equals 0. So what we have here is really a quadratic equation in lambda. Now, we need to solve it to find lambda. Can we use factorization? It's hard to remember the quadratic formula, you know. You might not be given the formula, that formula, on the formula sheet. Your formula sheet, I don't think it doesn't have the quadratic formula. Alright, yeah, if you say 1 by negative 3, two numbers that multiply to give negative 3, or 1, yeah, you could use factorization, alright? You could very well use factorization. You could also use completing the square. That would be interesting. It's nice to practice the completing the square, you know. Let's try that. You have lambda squared plus 2 lambda, leave a little space, minus 3 equals 0. You want to make this a complete square or a perfect square. You remember what you add to it? You add half the coefficient of x squared. The coefficient, well, in this case is not x, is lambda. The coefficient of lambda is the number that multiplies lambda, which is 2. Half of 2 is 1, so you add 1 squared. Alright? Now you add 1 squared to the thing. You need to compensate by subtracting 1 squared. Now you have this part just as you want it. And you remember, here, this is like you have x plus h squared is equal to, let me write this on the left, you have x squared plus 2hx plus h squared. See that? Now this part is like this part. You have to practice these things to remember them, you know. Now, in this case, 2h is equal to 2 because 2hx. Well, in this case, is lambda we're dealing with. So h is 1. H squared is 1. So h is 1. Alright? Once you remember the pattern and you've been practicing, you should see it. So x plus h squared is like x plus 1 squared. Now, minus 1 squared. Right? So you say minus 1 minus 3 is minus 4 equals 0. So x plus 1 r squared is equal to 4. Square root both sides, you have x plus 1 is equal to positive and negative square root of 4, which is positive and negative 2. So x is equal to, subtract 1 from both sides, you have negative 1 plus or minus 2. In one case, x is equal to negative 1 plus 2, and in the other case, x is equal to negative 1 minus 2. So x is equal to 1 and x is equal to negative 3. Oh, I put x. You see, my is really lambda. It should be. Alright? So it should be lambda plus 1, because I mix up the x here. It's lambda. So all of these x's is really lambda that they should be. Alright? So it's lambda, lambda, lambda plus that, lambda plus that, lambda plus that. Right? Now, of course, I erased the x's and changed them to lambda. But if you mix them up in exam, just put up here that let lambda equal x, and then after you put the x, you can't change back the x to lambda, because you already said let lambda equal x. Lambda and x would be the same thing. So you would need to erase all of these. Alright? So what you could do is when you have all these x's, if you are so accustomed to using x like I am, you see that you could say let lambda equal x temporarily is x. I say therefore the answer is lambda equal 1 and lambda equal -3. Alright. Alright. But as I said, you could have used factorization to do it. But I use completing the square, which is more work, but you should practice your completing the square. Alright, so that's it. I'll see you in the next video.